Alright, let's look at our last section, 9-6, and see how we're gonna conclude this chapter. So far we've seen two types of problems that have exponents in the variable. So everything we're doing has to involve solving for an exponent in the an exponent variable. How do we get, from a t being up here, how do we get down the bottom to be t equals, and so on. Same thing with k. How do we get that down to the bottom so we can get k equals? And we introduced the idea of, well, a logarithm. So we can take a log, we say, of both sides. And that'll keep the equation equivalent. And we introduced plenty of rules to accompany that. One of them being that if we're taking a log with an exponent, that exponent actually can come down here and become just a coefficient, just being multiplied. And then we went over the reasons for this back in the last lessons. Okay. And we can just treat this log just like a number. It's just an irrational decimal. Okay. So I can divide by it like any other number. Log of and then use your calculator, and this will cancel out just like any old number. So we now have t equals, again that was a goal, take that variable exponent, get to be just a regular old t, and we'll have to approximate that, so I'm actually going to use approximating. Anytime I use a calculator and round. Alright, so I'll have to do fraction, and I'll do log of 0.5, okay, go down, and log of 0.89, enter, and we get approximately 5.9480, almost 6. And just recently, end of last week, we introduced a new type of base called e, and e was a number that's kind of like pi. It has a decimal associated with it, 2.71828, very special type of base. And unlike this, which is base 10, okay, we're going to be using base e, so instead of a regular log, we want to take what was called a natural log, ln. Other than that, all the steps are identical. We're not going to do anything different. And we still have that exponent is now going to become a coefficient. So a negative 507060k. And the natural log of e, which, since this is base e, this is saying e to what power equals e. Right, that's e to the 1, so the answer here is simply 1, and it cancels out. And that's going to be equal to a natural log of 0.5, and again we can divide both sides and solve. Alright, so I'm going to do the natural log of 0.5 equals, and divided by this big number. Oh wow. So we get 0.00012, and that's what's equal to k. Some of your calculators might put this in scientific notation. Okay, so that would be 1, 2, 3, 4. So that would be 1.2 times 10 to the negative 4. Negative because it's a small number. Any number less than 1 these are negative exponents. If this was a real big number, it'd be positive exponents. So calculator might say that. Okay, it means the same thing. All right, so we're going to use this today, just solving some word problems involving increasing and decreasing. Okay? Increasing and decreasing. We looked at this actually in the beginning of the chapter, 9-1, so we're finishing where we started, full circle. And let's actually look at this with the formulas in mind. All right. So we said that we have an equation of this form and graph it. Okay. We saw that it either went up, which we called growth, or it could also have gone down, which we called decay. Growth or decay was associated with a b value, this b value being somewhere between 0 and 1. And the growth was associated, it was growing, the b value was bigger than 1. Okay. So looking at these two, you can see, well, 1 minus r, and the trick is here to notice that, well, growth is anything below 1, so this is 1 minus any number. Well, 1 minus any number is going to be below 1. So this is a giveaway that this is a decay formula. Same thing here, this e to the negative k. Also, so that's some number between 0 and 1. So these are your two decay formulas. And rightly so, over here you can see, well, 1 plus r, anything above 1, is going to be growth, so 1 plus any number is going to be growth. Okay, so you have two choices to make for each word problem. Are you going to be using this kind of formula, or this kind of formula? Okay. And we have, is it decay or is it growth? Which one is it? So a couple of decisions to make for each graph. We'll go over which ones to use. In general, if you look at what the difference is, that this has an r. So r is usually given as a percentage, so if it's a percentage problem, you'll know that, well, I got to use either of these, depending on its growth or decay. And on the other side, if they don't give you a rate, probably means it's going to be just the rate of e. So the rate has to be given, and if it's not given, then you're going to use one of the formulas involving the growth of e. And these e's are going to be involving a lot of things with bacteria decaying or carbon dating and things like that. So we'll get the hang of it after doing some of these and which ones tend to be what kind of formula. Recall that the a here and here was the y-intercept. Okay? And for our purposes, it's also going to be thought of as our starting. So we'll be doing problems with money and saying, if you have this much money, how long will it take to get this much money? So think of that starting point. You know, here's how much money we already have as our A. Okay. Again, we already said R is like the rate. Little side note, if you're given a rate of 10%, make sure you use 0.1. If you're given a rate of 5%, make sure you use 0.05. Always enter as a decimal. Time, you know, this can be anything. You know, this can be years, months, weeks, depending on the problem. Note that's what we're going to be solving for. Time is in the exponent, and that's why we need logarithms. So a lot of these questions will involve, how long does it take for us to get this much money? Or how long does it take for the house to gain this much value? So we're always interested in how long it takes. Okay, and K, you can see that is in only the E formulas, and that's a sort of constant we'll be solving for. Sometimes it's going to be given to us. So for instance, there's a problem with carbon-14, and we'll just have to know that the K value is this. Okay, so let's look at a few of these. I'm going to be focusing mainly on us choosing the right formula and setting it up. Most of the work afterwards is just stuff that we've already done. So my main focus is, let's see, our selection process. So if we read this, it says, okay, it's a sale, certain type of digital camera, original price, okay, y-intercept, starting place, original price, 198. Price decreases by 10%, okay, the percent lets me know that's an R. And we had a y-intercept here, that's an A. Price decreases by 10% each week. Our cameras sold. How many weeks will it take for the price of camera to drop below half? Drop below half the original price. Half the original price. The original price is 198, so we can replace half the original price with $99. So you can see that once again, what are we going to be finding in all these problems? It's a time. How many weeks will it take? How many weeks time? Alright, so which formula? Is this growth or is this decay? So if we can see, we're starting at 198, going to 99 eventually. We know it's decay. So, and then the fact that they give us a rate of 10%, that lets us know that we're going to be using this one. So I'm going to start off with the formula, then I'll plug everything in. Alright, so we have our y-intercept, A, 198, our starting point. Our rate of 10%, so remember, convert to a decimal, 0.1. And that we want to know when this is going to get to $99. Okay. Alright, now we just need to solve. So from this point on, it's just a regular old logarithm problem we're going to be solving. So let's see here. Let's get the 198 to the other side, divide both sides by 198. We'll have 99 over 198 equals, and this is going to be 1 minus 0.1, it's just 0.9 t. Take the log of both sides. We should do a log of this fraction. So we'll have, let's see here, log of 99 over 198 equals exponent becomes coefficient t times the log of 0.9, and then go ahead and divide both sides by that coefficient log of 0.9. Okay, and again, this will be approximation. Let's go and plug it in. Let's see, you gotta be careful. So I want to do fraction here. Do the log of 99 over 198. Close that parentheses. Do log of 0.9. We're looking at about, let's see, 6.5788 weeks. Alright, and they're not probably going to discount this in the middle of the week, so we're looking at about 7 weeks. Let's say 7 weeks for good measure. In the 7th week, it'll go somewhere between a little bit above $99 to a little bit below $99. So about 7 weeks. There you go. Once again, you'll notice that the really only thing new here is the formula decision and plugging in the values. Other than that, this part is everything we have been doing. Okay? Maybe this answer you have to think about sometimes, just what it means. Like, like 6.5 weeks, will they actually mark down a price at halfway through a week? Usually not. Usually it's once a week or once every 2 weeks. Other than that, most of the review. Alright, so we have a carbon 14 problem. Okay. Now we do have to reference actually one of the examples where they solved for a K value. And I don't give it to you here, but it's 0.0012. So given that, it's pretty obvious that we're going to have to use one of the formulas with K, a K value, constant. And we're starting at 150, that's our A. We're ending up at 130. So since it goes down, we're looking at decay. So we want to use the decay formula. So we'll have, let's see, write this down. Plug all our values in. We know 150. We know K is now going to be negative 0.00012. T, we don't know time. I mean, this is going to end up at 130. Alright, so we just need to solve this. Since we're using the E value, we're going to use the natural log of both sides. Okay, similar to the last problem though, we're going to divide both sides by 150. So I'll have 13 over 15 after I cross out the zeros. Okay, will equal all of this. We'll take the natural log of both sides since it's base E. Okay, so I have natural log 13 over 15. It's going to equal, okay, I'm going to bring the exponent down, negative 0.00012 t. Right, and remember that L to the base E to the E equals 1, so that will cancel out. Divide both sides by that long decimal. And let's calculate. Okay, let's see here. So fraction, natural log of 12 over 15 and divide by negative 0.00092. Alright, so we get approximately, let's see, I'm going to go with 0.5 approximate. Okay. And the question asks, how old is a fossil? And we'll assume that this is a years unit by default. Years. There we go. So there's a carbon 14 problem. Just remember that K value may not be given. It's in one of the first examples in the book, but in where all the problems are, it's not given. You need that information. Alright, there's another one. Once again, we're going to try to figure out what formula to use first. We have an increase. Alright, so that increase alludes to growth. So we got here or here. And it's given us the rate. Alright, so that narrows it down pretty fast. So we got y equals a 1 plus the r to the t power. Let's plug in our values. What we know so far, we only know the r, so 1 plus, be careful, 0.04. Not 0.4, 0.04. And we purchased the home 8 years ago for $122,000, and we want to know what the value is right now. So our initial was $122,000. So really, this isn't 8 years ago. So really, we're not even solving for t. They tell us that the time is 8 years. So we're just trying to really just plug this in the calculator and see what we get. There's no logarithms involved. Only if we're trying to find out what t is would we have to use a logarithm. There we go. 1,222,000, okay, times 1.04, and that's going to be raised to the 8th power. Alright, so this house is now worth $1,666,965. Approximately. That'd be y in this case. So y we solve for. So in 8 years, I subtract the original. 8 years of owning the house, it's gone up about $45,000 in value. 8 years, $45,000 made. Alright, let's see here. Lastly, looking at bacteria, I mentioned this before. This time they tell us the formula pretty clearly, so we just need to do what? According to the models, how many hours will it take for the amount of B1 to exceed the amount of B2? Alright, B1, alright, I see, B1. When will B1 be bigger than or greater than B2? That's really what they're asking. So, when will B1 of t be bigger than B2 of t? Alright, we just have to solve this inequality. So we have what, 1200 e to the 1532 t, and that'd be bigger than 3000 e to the 0.0466 t. Alright, when will that happen? Alright, so let's set this up. We need to get the numbers on one side, regular numbers, and the e's on the other side, so I can take the natural log of both sides. So I'm going to divide both sides by 3,000. Okay, I'll put all these big numbers over here. Okay. I'm also going to divide both sides by this e, this one, so I'll have the e's on this side. So it's kind of like I'm moving the numbers to the left, and I'm trying to get the e's to the right-hand side. I'm trying to get those together, so I'm trying to group all the stuff that's similar together. Got these a few more algebra properties than we normally do, but nothing we can't handle. So now this is just 1. This is just 1. 1200 over 3000. This will just, these zeros will cancel. 12 over 30 reduces to, so divided by 6. 2 divided by 6, 5. So I got 2 over 5. This needs to be bigger than this. Alright, now this e might be confusing, but just think about, you know, any base, the rules for any base, and forget the decimals. What if this was, what if this was, you know, 10 to the 6 over 10 to the 2? Alright, that's a 6. What would you do? You'd say, oh, that's 10 to the, you know, 6 minus 2, that's 10 to the 4. I just need to do the top minus the bottom. So we're going to do the same thing. It's just, it's a bunch of ugly decimals. So it's going to be e to the, let's see here. It's going to be e to the, I just need to subtract the top minus the bottom, so I'm going to do 0.0466 minus 0.1532. Alright, so negative 0.1066. Negative 0.1066t. Okay, so yeah, we had to do one little extra step with this E business, but from there on, similar to every other problem. Okay, so we're going to take the natural log both sides. And so 2/5 must be greater than, and that come on down to the front. And the natural log of E, which will actually equal 1, and divide both sides by this negative. Point 1066. So here we go. Let's put that in and see what we get. Natural log. Natural log of 2/5 and divided by negative 0.1066, and we got about 8.596, we'll call it. Yeah, about that. So about a little over 8.5 years. 8.5 years. Go. Oh, 8.5 hours, sorry. Yeah, I look at the units of the question, so we're looking at hours. That makes a little more sense, too. It's a long time to grow bacteria. There we go. Alright, so we've seen sometimes picking the formula is easier than others, like on this one, they give it to us straight up, but we might have to use some other, Algebra 1 techniques. Just remember, even with all this new stuff, it's still using the same formulas as it has been for a long time. Hope it helps. Keep in mind the only thing that's new here is make sure we know which formula to use. Okay, after that, we just have to play with anything else. So if you ever get stuck, ask yourself, are you using the right formula? Is it really growth or really decay? And that should help out a lot. We'll spend tomorrow going over all the problems. Good luck.